Hello, I'm going to discuss my solution to the LeetCode problem House Robber 2. It's today's problem in the October LeetCoding Challenge. I'm Channa Bankapur from Go Master Technologies. The problem definition is as follows. We have a bunch of houses arranged in a circle, and each house has a certain amount slashed in there. And uh, a robber wants to rob as much as possible, but there is one constraint, which is if two adjacent houses are broken into the same night, then there'll be an alarm which is going to be set out. So he wants to avoid that part, right? So knowing that, how much he can actually rob, what is that maximum amount the robber can rob, right? That's the problem here. If you take this example of 232, the answer has to be 3 because he cannot rob any two houses because they are either adjacent to each other in the row, or the first and last is also adjacent because it's in a circular way, right? So that's why he can only rob one, and 3 is going to be the answer. If they were not in the circular way, then he would have robbed first and last, so maximizing to 4 units, right? But yeah, on the other hand, so because of the constant, he can only rob one. There is an easier version of this problem called house robber in LeetCode, and that does not have that way of the circular way of arranging the houses. It's all just row. So in that example of 232, the robber can actually choose first and last because they're not adjacent, and the answer is going to be 4 for this, right? So it turns out the solution to this one is needed to solve that, at least the way I'm solving it. So let me explain the solution to this, and then I'll relate to that, right? It's going to be straightforward once we solve this, right? It's a small modification to that, right? So here is my solution to just the house robber problem. It's also called coin row problem because the values or the amount stashed in every house can be considered as just a coin value. And so it's just a row of coins, and we need to pick as many coins as possible, maximizing the amount with that constraint, right? So essentially, we need to find the optimal subset because it's going to be a subset of these set of coins. Which maximizes the sum of integers in that subset, but the constant is no two adjacent integers in this initial array can be included in the subset, right? In this example, it turns out, picking these three, 9, 6, and 8, which is going to be 23, is the maximum thing we can get. We cannot get more than 23 for this problem with the constraint. All right. So let's see how does it work. The way I'm working out is I'm using the idea of backtracking to start with. So this actually resembles whatever the tree I'm going to write is going to resemble what's called state space tree. So now, so the idea is, suppose we have a problem here. The problem has 7 items in that. And the solution we are going to build is basically empty at the moment. That the subset we are going to build, the optimal subset essentially. But yeah, so what we are going to do is we try to be exhaustive here, trying all possible cases and see what happens, right? So in this case, the way I'm approaching here is I see whether the last item to be included or not, right? So those are the only two possibilities which cover all possible subsets, right? Because in some subsets this item is there, in some it's not there, right? And we want to find an answer which has in either of those cases, and then get the max of these two possibilities. That is what being exhaustive means. So if I choose the last item, if the last item is part of my solution is going to have this. And then because it is already chosen, 8 cannot be chosen because it is adjacent. So that's why the remaining problem is going to have only the first 5 items, right? If I don't choose the last item, if the solution does not have the last item, then the solution so far is still empty set. But the last item we just didn't choose it, so we have the remaining 6 items to choose to solve from, right? So we're going to solve that. So if you see here, there is already subproblems which are also of the similar type, which has a subset or a set to be solved, and then a partially built subset, which is the answer, right? Which satisfies the constraint, right? So if you go further, it's going to look like, right? So with and without two possible cases every time you do, based on the last element in that input, right? So the last element here is 3, and here it is 8, right? Likewise. So if you go further, this is how it's going to look like. And so we have got some few answers here. So if among them, look at all the leaves we have got here in this kind of tree we have constructed, where the input becomes empty. That means there is no more elements to be processed. In that case, whatever the subset we have got is an answer, right? Is a solution that satisfies the constraint. Doesn't mean it is optimal. Not everything is optimal, right? So these are all what is called feasible solutions. So look at this example, 9435. It looks like it's a good choice because it has 4 elements, and that is the best way to take it, right? Every odd element I'm taking, odd indexed element I'm taking here, right? 9435. But that adds up to 21, which is not optimal, right? So and then if you take all the even elements, even numbered elements or even positioned elements, 268 is also not very good. It's only 16. But yeah, 968, where it is one of them is an odd position and the other two are an even position, looks like a good choice here, right? That is optimal, which is 23, right? So this method is what is called backtracking. If you just go through all of these things, every leaf is going to have a feasible solution. You keep track of the best found so far. When you complete the whole search, you're going to have basically the optimal solution, right? So that's the way to solve. But yeah, I don't want to solve this way now. I'll turn it around. Instead of leaves giving me the answer, I'm going to I'm going to start building the answers from leaves, and then they are going to get me the answer at root, right? So that's basically the reverse way of doing it. So here I'm calling that as a function f, which is going to have this input of these n items. And so f is my optimization function now. So these subproblems are going to return that answer to me, whatever the answer to their subproblems. And what I'm going to get here is going to be the optimal answer, right? So that's how I'm going to build from bottom to top now. That means this is what is called top-down solution in a way. So as usual, I'm going with the last element and then without the last element in these two paths. And if you look at with, I didn't actually give any name to this node, but yeah, I just processed the last element Cn minus 1. What about Cn minus 2? Now the choices for Cn minus 2, there are not 2 of them in this case because we already chose Cn minus 1. Cn minus 2 cannot be chosen. That's why with path is essentially going to be pruned out, right? So any of those subsets we get are all going to be infeasible. So this idea is called branch pruning in backtracking. So, but without is the only choice. So I'm going to go with this. And obviously, when I say with last element, the value of this one is going to be added to the solution of this f of n minus 2 elements. If I go in without path, it's going to be f of n minus 1 because except the last element I'm choosing it, right? So this is going to be the recurrence we are going to derive. So recurrence is going to look like this. So f of n, that means the solution to the first n items is going to be max of last item plus f of n minus 2 or f of n minus 1, right? One of these two is going to be the answer, right? Because it's a recurrence of order 2. So we need 2 base cases. F of 0 is going to be 0 because if there are no items, the answer is going to be 0. But if there is only one item, constant is not going to affect us. So the answer is C naught, only the value of the first item, right? So implementing it as it is, it's what is called backtracking solution. But yeah, strictly it is not, but it is kind of resembling the backtracking solution. So it is just implementing as it is. So see rob of this whole array. If n equal to 0 or 1, these are the base cases we have seen. Otherwise, we are going to solve these two subproblems and take the best of those two, right? And we can analyze this kind of recursion tree and see that it actually takes big O of some 2 power n, right? It is actually, this is just an upper bound, but yeah, in the worst case, it is going to be 2 power n, all right? So yes, the space is big O of n for the function stack, right? So let's, this is obviously not the solution we are interested in. So if you see what went wrong here, what is that so inefficient thing here in this case, if at all there is one. If you see here in this tree or in the state space tree, every node is solving a function f, right? Actually, if you see this example, that will be more clearer. Every node is solving a function f, right? So that's why there are like exponential number of nodes we are solving. But do we really have exponential number of problems to solve? If you look at f of n, what is the possible values of this parameter, right? What are the instances we end up solving? F of 0, f of 1, actually these two are base cases, but f of 2 onwards are the problems we need to solve. it can go only up to f of n. That means there are linear number of problems to solve, but we are solving exponential number of them. That means there is overlapping subproblem that can be observed. If I just draw this recursion tree for f of 6, you see that f of 4 appears twice, f of 3 appears thrice, and f of 2 appears 5 times. Actually, the number of times these problems appear is going to increase again exponentially, right? Actually, in the way the Fibonacci sequence goes, right? So that means there is overlapping subproblem. We are solving the same problem multiple times. One simple idea is why not just remember answer to something, like suppose f of 2, once you remember it, do not solve it again and again, right? Once you solve f of 3, don't solve it multiple times. So maybe you should solve this one, but not this, right? These are something I should use already whatever is solved. And once I solve this, I don't have to solve these two. Actually, when I don't solve this f of 3, this will not even going to be called, so don't worry about that part. So, and then once we solve f of 4 here, this should not be solved. So even this f of 3 is not going to be called. This whole subtree is not going to be called, right? So that is the idea of what is called memoization. I'm going to use a table. So this is the pictorial way of understanding how it looks like. So we are going to have a table of all possible answers from f of 0 to f of 6. Some people call it as DP table informally, but yeah, that's the idea here. So I initialize with the base cases here, f of 0 and f of 1. We know the input has the 6 elements, and 9 is the first element, and then I have included this already. So whenever we want to solve a problem here, so we call here, we see whether it is already solved. If it is solved, we directly fetch it from the table. Don't go recursively. If it is not solved, solve it recursively, right? So that's the idea. So f of 6 is going to call f of 4. That's going to call f of 2, because none of them are solved at the moment. It calls f of 0. That is already a solution, right? Doesn't matter whether it's base case or not. The solution is available. So that's going to give me, and then f of 1 is also available. And when f of 2 finds the answer, it is going to update the table so that the future calls to this f of 2 does not have to solve it again, right? So similarly, f of 3 also doesn't have it. It's going to call f of 1 and f of 2. Look now, f of 2, earlier it was solved. That's why it didn't even call these f of 0 and f of 1, right? Because it was already available, right? So similarly, if you go further, f of 3 and f of 4 are going to be updated in the table. So that will be useful later. So now if you come on the right side, f of 5 calls f of 3 and f of 4. Both of them are already solved. That's why this whole subtree is not going to be called, right? So this is the savings in time in a way, right? So now that's how it's going to update the whole table, and then you have the answer at f of 6, right? So this is how memoization works essentially. It is kind of backtracking, just that you are not solving a repeated problem. You're using a table like a central repository or a cache. This is like more like a cache. You're going to try to access the cache. If there is a cache miss, you solve it and then update the cache, right? If it's a cache hit, directly fetch it from there. So that's how only the first time you access the cache is going to be expensive, but later on it's going to be simple or fast, right? So this one is a simple memoization. I'm going to implement here. Look at this. I have initialized the table with the base cases here, and all other non-base cases I initialized with some value which is not going to be a valid answer. So -1 is one of them, just to identify whether it is problem is solved or not. All I need is solution to a problem, a parameter of n, right? F of n. So that memoize of n is going to be f of n. So that looks at the table first. If it is not solved, it's going to solve. That means if it's a cache miss, it solves, right? And it solves and updates the table, right? That way, if it is a cache hit, it's going to be cache hit later on for the subsequent calls, and then it directly returns, right? So if you see here, even though this is recursive, there is double recursion. It looks like exponential time, but it is not. Why? Because this part of the code, which is in the if block, is going to be executed only the number of times this is -1. So which is only n-1 such locations have -1. And once it is solved, it's going to become not a -1 value. So that's how this part is executed only n-1 times. And look at this inside there, other than recursion, it's all constant time. So that's why it should take linear time. And it takes linear space also, one for the table size is linear here, and also recursion. We need recursion stack or function stack that also takes linear space, right? That's the solution here. But yeah, it's always good to make it bottom up and then implement it. So the idea of bottom up is you look at the table here, and we already know that each cell in the table is basically a solution to an instance of function f. So we need f of 6, right? But how did we get f of 6? You see the dependencies. That means they must have computed first, right? So this is the kind of dependency graph I came up with these instances. And this has to be a directed acyclic graph because there should not be any cycles. If there is any cycle, recurrence doesn't work, right? So if you look at this is a directed acyclic graph, and a topological order of this one is always good enough to compute from bottom to top. That way, anytime when you're computing f of I, so f of I, whatever it depends on are already computed before that. So you don't need recursion. You can just fetch it from the table, right? So we use the same table, just that we fill in this topological order. In this case, topological order is trivial, but yeah, otherwise that is the concept, right? So if you code it this way, it's going to look like this. I have the same table I initialized with these two base cases, and rest of the cases, I'm going to go through this loop and then update. Look at this. These are all direct table access, right? I don't even check whether it is there or not. It has to be there, right? Because it is topological order. So this runs exactly linear amount of time and pretty fast. So, and also space also is linear because of table. We don't have recursion here. So that is a savings, right? So if you implement this one, it's going to look like this. Let's see. Okay, here is the LeetCode problem. So yeah, I just have the solution here. Look at this. I took the number for convenience. N is the size of nums, and n equal to 0 and n equal to 1 are base cases. And then I allocated enough space for the table. Look at this table size is 1 more than the nums n, which is n plus 1, because it is from 0 to n, right? And table of 0 and table of 1 are initialized, and these are the this is the loop, and then finally table of n is going to have the answer, right? So this should work. It works pretty fast. If you see, look at this, it's all 100%, right? But if you, okay, let's see, how can we use this solution to that house robber problem too, right? So let me use this, copy this part, and then try to see how we can use it here. So in this problem, the only difference is circular thing is not allowed, right? So let me, okay, let me modify this part. Yeah, so what we have is only circular part is not allowed here. So that means if first and last houses are selected, that is not a valid thing. So in a way, what we need to solve is, we need to solve for a problem excluding the last house, right? That is the one. That means solve for f of n minus 1 essentially. And another one is exclude the first house and solve, right? This is also kind of f of n minus 1, but it is excluding the first and including the rest, right? So if we can solve these two problems, we can take the best of these two and then the answer, right? Why I'm not using a function f on this problem directly is because the subproblems are not going to be circular. Once we exclude one element, it is not a circular problem anymore, right? So what I'm going to do is in the same way, I'll solve here, but I'm going to exclude the last house. So for me, the last house is not included here, and answer is in n minus 1. So this is excluding the last house. So this I'm going to store in, say, without or actually excluding the last. Excluding last, right? So this is the answer I have. Now, how do I compute, excluding the first, right? So which should be similar to this. So in here, when I exclude first, what is this table of 1? Table of 1, we were selecting the first house. I'm going to say we never select this house, right? So now in this way, the first house is never selected, right? So that clearly excludes it. And now if I go till the end, I'm going to have f of n, or table of n is going to have that answer. So that's why I'm going to say return max of, table of n, table of n, and excluding last, right? So this should give me the answer. Let's check whether it works. It worked for the test case here, but let's see whether it accepts. It accepted. So it accepted, and generally it works fast here. you can check the speed in this case, how much time it took. So it runs in 100 percentile time because it's 0 millisecond, which is negligible. But let's see how we can improve from here, and not in terms of time, this is the lower bound, but can we improve the space requirement here? Do we require all this space? If we needed those, the subset of houses to which the robber is going to rob, then probably we need to go further from here and we cannot optimize. But what we need is just that number, right? So for that, we don't need to remember the whole table. So look at the table here. When I'm computing f of I, all I needed was I minus 1 and I minus 2, right? I didn't needed I minus 3 and anything before that, right? And when f of I is computed, when I go for f of I plus 1, I don't need I minus 2, right? So all I need is this window of three values, and we can slide this window, right? So that's why the whole table is not necessary to be remembered. I just need to remember three values, which is the previous two values, and that's how I'm going to compute the current value. So the previous two values, probably I'm going to call it as table 0. So it's not going to be a table essentially, but I'll still give the variable name like table 0, table 1. It is now a variable name, not an array index. So, but here ith one is going to compute it, so I'll just call it as table I, and table I minus 2 has to be 0 here, and then I minus 1 has to be table 1 in our way of getting it, and table I is I. So now table I'll compute it this way. So this way I'm using only constant space here. Okay, what is going to be n minus 1? The last one. The last one has to be table I is not even accessible outside. So, but yeah, we need to slide the window, right? So the sliding window is an extra effort. So that means table 0 is going to get table 1, and table 1 is going to get whatever is computed just now, which is table I, right? So the table I is like a local variable, and table 1 has the recent value, and that is the answer here, right? So if I do the same thing here again, that should work in the exact same way. So probably I can copy paste this in the code inside here. That should work here, right? So table I, okay, all of this is going to be same. So now what I need is, yeah, the table 1 is the recent answer, and excluding last has to be the other answer, right? Let's see. I think there is some compilation error. What happened? Okay, these are variables. I should declare them as int here, and even table I is also a local variable here. I need to declare, right? Okay, there is still some compilation error. Yeah, I think I had. So what I needed here was so table 1 is computed, right? Table I is computed here. Okay, if table 1 is greater, table 1 has to be the answer here, and here also table 1. I just missed that table 1, writing 1. Okay, there is still more errors here. Table 1 of 1. Okay, it's not an array, it's just an integer. I'm sorry for so many typos. All right, so it got the answer, and let me submit. It accepted. So it accepted, and it should run fast. Actually, it's not about the time. It should take lesser space, but I'm not sure space is going to be so much visible. 8 MB is pretty much the the minimum amount of space it requires, and that's why space improvement is not very much visible here, right? Otherwise, asymptotically, we know that it has improved. All right, so that's the solution. That's my solution, and let me know if you have any other way of solving this one, or any better way of solving this one, and if you have any questions, any comments, suggestions, please put down in the comments below. All right, so please like the video and subscribe to the channel. And this video is going to be in both playlists, October LeetCoding Challenge and also Dynamic Programming list. I have a playlist for backtracking and dynamic programming solutions, so it's going to be there. So do watch other videos in the playlist. Right? Thank you for watching. Happy coding.